Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we're going to be explaining our compile time counter, which we first introduced at CPPCon in 2015.
So let's see how this works.
Compile time counter using templates and const.expr.
In order to support the signal slot system in CopperSpice, we really needed to implement the basic features of reflection. Reflection isn't currently part of the C++ language, but we wanted to do this using native C++. These ideas are not just about reflection. They may be relevant to any code that you're working on.
We tried various approaches, and we had one idea we were using for a while, and then we discovered it was not standard compliant. What we ultimately realized was we needed to implement a compile time counter. This is what we're going to show in the video. And future videos will actually discuss how we use this technology to implement signals and slots, full reflection, and the meta object system.
Since we use constructs like const.expr, this technique required a minimum of C++ 11. We could not have done this in an earlier version of C++.
So here's the dilemma we want to solve. Given that we have a method called cs_register, we want it to do something. And then when it's done, we want it to call the next cs_register method. The question is, how do you implement this?
So our idea was to set up a chain of function calls. We'd like to structure the code something like this, where we have a set of cs_register methods, and each one calls the next one. The problem is, this code can't be generated from a macro, and there was too much of it to write by hand. So the question is, how can we take this pseudocode and translate this to something which can be implemented in C++?
So here's the idea we came up with. The method cs_register would have a pass parameter of 0 on the first call, and then when it is done, it'll call cs_register passing the parameter of 1, and so on. And again, this is something we wanted to happen at compile time. So how do we implement this?
So just as a review, the first thing we're going to be talking about is const.expr. Const.expr is a way of marking an expression for compile time evaluation. And in this example, you can see we're marking a variable as const.expr, which means it is guaranteed to be known at compile time, so it can be used as the size of an array. Without const.expr, this is not a compile time value, and so this array size is invalid.
Normally, the idea of a template is to pass a data type, and that is received by the template method. The question is, do you have to pass a data type? Is that the only thing a template can understand?
And the answer is no. You can pass an integer value as a template parameter. And it's very important to understand that passing an integer to a class template creates a unique data type. We can use this mechanism to wrap an integer and set up a data type that we can then use to solve our problem. So how do we do this? So here's the first part of the mechanism that we came up with. We have a templated class called csInt, and it takes a parameter that is an int, n. And let's first look at the general case. A csInt of n inherits from csInt of n-1. So this means if you have a csInt and you pass 3, it will inherit from csInt 2. Now, in order to stop this recursion, we've specialized the class template for 0. You'll see that csInt 0 does not inherit from anything. So this means if we declare a csInt 3, it will inherit from 2, 2 inherits from 1, 1 inherits from 0, and then the inheritance stops at the 0 level. The whole purpose of this is to define the data member named value, which is a const.expr int, which will return the original n that the template was invoked with.
As an example, Ginger would be a class located in your application. The two static methods shown on this slide are actually expanded from a macro in CopperSpice.
The cs_register method is a template that will accept any wrapped integer and do nothing. This will be used to terminate the chain of method calls. The CSCounter method is a method that takes a wrapped 0 and returns a wrapped 0. The purpose for this may not immediately be apparent, but it will be explained shortly.
We wanted to briefly mention the CS_token_paste2 macro. What this does is it takes a value and the line number that appears in the code. This is part of macro expansions and not really part of the information we're showing. But where you see the value _42, that is generated from this macro.
So let's take a look at the declaration of value _42. First of all, it is a static const_expr const_int data member that's been injected into your class. But what's interesting about it is the value that it contains. So looking at the right side of the equal sign, the first thing I see is a decal type. And whenever I see decal type in code like this, I think we're asking a question of what if? What if I were to do this? So now let's unpack this expression from the inside out. The question we're asking is, if I were to call CSCounter and pass it a wrapped 255, what would it return? Well, the decal type asks not what value it would return, but what is the data type that it would return. Then after using decal type to retrieve the data type that CSCounter would return, we use : value to retrieve the integer value stored in that data type. Then on the following line, we declare an overload of the CSCounter method that takes a wrapped integer and returns a wrapped integer. Then you'll see that the declaration of value 43 is exactly identical to the declaration of value 42, as is the subsequent declaration of the CSCounter method. The question is, what is value 42 and what is value 43? What are the values that these are initialized with?
So how do we calculate value 42 and value 43?
So the first thing we have to look at is, as I mentioned, we're asking a what if question. Well, if we call CSCounter at this point in the program with a wrapped 255, there is no overload of this method that takes a wrapped 255. So the compiler needs to look for the best match. And 255 inherits from 254, which inherits from 253, which goes on up the chain until eventually we get to 0. There is an overload of CSCounter that takes a wrapped 0. This is a valid match, and it's the best match that's available because it's the only match. This overload of CSCounter returns a wrapped 0, which means the decal type will evaluate to a wrapped 0. Then we apply the : value and we receive an actual integer 0 value. So value 42 is initialized to 0. If you didn't see where we set up the 0 version of CSCounter, go back a slide and you'll see it there. Now, we declare a new overload of CSCounter. And since value 42 is 0, value 42 plus 1 is obviously 1. So we're declaring a new overload of CSCounter that takes a wrapped 1 and returns a wrapped 1. This means that down on line 43, when we're initializing value 43, the answer to our what if question is going to be a wrapped 1. The reason for this is because 255 is slightly closer to 1 than it is to 0. So the overload of CSCounter that takes a wrapped 1 is a better match for 255 than the overload that takes a 0. Therefore, the decal type evaluates to a wrapped 1, and the value gives us an integer 1. We then go on to declare an overload of CS counter that takes a wrapped 2 and returns a wrapped 2. And we can continue in this fashion. Now let's look at the additional code that's expanded on line 42 that actually uses the counter value.
So the first two declarations on this slide are the exact same as the ones on the prior slide.
What these allow us to do is now declare the CS register method, which was the purpose of this mechanism. And as you'll see, we've declared a CS register overload that takes a wrapped 0, because value 42 is 0. It does some work. The exact details are something that we'll explore in a later talk. And then it goes on to call CS register, passing a wrapped 1 as the parameter. You can now see that this CS register method will call the CS register that takes a wrapped 1. And we will continue the chain until we fall off the end, at which point it will fall back to the templated method that we defined at the very beginning of the class, which will do nothing and terminate the chain. So an interesting point comes up when we're at this place in the code, which is that value 42 must depend on the result of calling CS counter, and it must be able to only see overloads of CS counter that were already declared. However, in the CS register method, we must be able to call an overload of the CS register method that has not yet been declared. How can these both work? And the answer is because of the rule in C++ for when a class is considered complete. Once a class is considered complete, all of its methods and data members are available for use. Before it is considered complete, only the methods and data members that appear above the current line of code are available for consideration. It turns out that the rules of C++ allow our example to work perfectly.
The rules of C++ specify when a class is complete and therefore when it's visible. One of the most obvious places of class completion is at the end of a class.
But there are other places within the body of a class where the class is still considered complete and you can see things that were declared below the current location. One of them is inside the curly braces of a method definition. And so this second highlighted area, where we're calling the version of CS register that has not been declared yet, falls into this category and works perfectly. Another case is after the equal sign that declares the default value of a method parameter. This doesn't occur in our code. Another case is after the equal sign of a static non-const data member initializer. Notably, that rule says non-const. Since value 42 is a const data member, this rule doesn't apply, and therefore, after the equals sign, this decal type can only see overloads of CS counter that have already been declared in the class. So everything you've just seen is compliant with the C++ standard and will work correctly. Not only that, but it is extremely efficient. Since the call from CS register to the next method in the chain is a tail call, it can be optimized. And in fact, if you compile this with a recent version of Clang, this entire mechanism is compiled away, and all of the registration code is inlined into one method with no overhead.
So what we have shown you is our compile time counter that we actually do leverage and use in CopperSpice. But this code can be used anytime you want to generate a sequence of values from a macro.
For more information about CopperSpice, please visit our website at www.copperspice.com.
Thanks for watching our video, and we hope you found the content of value. If you have any questions, feel free to email us or leave a message on our CopperSpice form. We really do look forward to hearing from you.
Please make sure you subscribe to our YouTube channel and come back in 2 weeks for our next video.